This screencast is going to walk you through the derivation of our four kinematic equations. Um, we can get them from graphs, and we can also get them from algebra. This is going to be focused more on the algebra. But to start, though, we are going to start with our graphs. The first graph is the velocity versus time graph. And in our lab, we had a air cart sliding down a inclined ramp. And we found that our velocity versus time graph looks something like this. Maybe if our velocity was 0, the y-intercept would be 0 here, or the initial velocity. But we had a line in a positive slope. And in math class, the equation for this line would be y equals mx plus b. But these variables don't really mean anything to us in physics. They have some meaning, though, in this context with this graph. So we want to use variables that mean something to us. So instead of y, we have a v. And looking at the slope, we'll skip that for now. But the x, instead of having an x on our graph, we have a t. And the b is our y-intercept. And now let's think about what this means. The y-intercept gives the value, on the y-axis when the x variable is 0. So in this case, our x variable t is 0. It gives us the velocity. So the velocity at time 0, another word for that, is the initial velocity. And the symbol we use is v naught for that. It's a v sub 0. And now let's look at the slope. Our units for the y-axis were meters per second. And on the x-axis, the units were seconds. So the units of the slope are going to be units of the y, so meters per second, divided by or over the units of the x, seconds. So this is meters per second per second. And remember, slope tells you the change in the y over the change in the x. So this is the change in velocity over the change in time. Another way to say this is how fast is the velocity changing. And the word we use is acceleration, and the variable we're going to use is a. So the slope of our velocity versus time graph is the acceleration of the cart. For the units, we can think of this as meters per second per second. You can write it this way. Some people like to write it like meters per second per second. Or if we go kind of from this writing here, when we have fractions within fractions, dividing by this s is the same thing as multiplying by its reciprocal. So instead of dividing by s, I'm going to multiply by the reciprocal of s, which is 1 over s, which is going to give me m times 1 is just m, so meters, and seconds times seconds is seconds squared. So you can think of, I'd like you to think of acceleration, the units of acceleration, as meters per second, but when we write them, sometimes if you want to take a shortcut, meters per second squared works as well. So this is our first equation, our first kinematic equation. The second kinematic equation is going to come from this graph as well, and it's going to come from the area under the curve. So if we kind of section this off here, and we learned from our last unit that the area under a velocity versus time graph is displacement. So area is equal to our displacement, which is our delta x. And before it was just the area was a rectangle, length times width. It was very easy to do. But now it's a little bit more complicated. This is a trapezoid. And if you remember from your math class, the area of a trapezoid, the formula, area of a trap, that formula is 1/2, and then you have two bases, base 1 plus base 2, times the height of your trapezoid. So this is an area for a formula of a trapezoid. It doesn't work for physics, though, because what's base 1 and what's base 2? So let's figure that out. What you actually have to do with this trapezoid is turn it, kind of rotate it on its side, because I think a lot of times you see a trapezoid, we have one base, we have another base, and then we have the height here. So if you sort of spin this, it may help you see this. But the bases are the two parallel lines, so we have a base here and a base here. So we'll label this base 1, and this is base 2. Let me erase this other stuff, get this out of the way here. But instead of base 1 and base 2, we need to use some physics variables there. So what are the physics variables? So actually, let's take out this base 1 and base 2, those labels, and put some physics variables in here. Well, what is this point right here? Well, this is the y-intercept, which is our initial velocity. So instead of base 1 or base 2, let's call that v naught. And this point right here, we want to know this distance from the t-axis all the way up to, well, whatever our velocity was at the end. What variable do we use for that? V. So from here to here is v for our final velocity, or the velocity at time t, and then this is v naught. So there's our base 1 and our base 2, and then the height, which is this side here, that is going to be our time, however much time the object moves for. So we have t. So our area is equal to delta x, which is 1/2, base 1, which is v naught, doesn't matter actually which one we choose, plus base 2, v, times t, which is our height. So v naught, t, and v. So this is our equation number 2. Let's write all our equations up here. Or actually, we'll do that on the next thing. So equation 1, v equals at plus v naught. Equation 2, 1/2 quantity v naught plus v, closed quantity times t. Both of those come from our velocity versus time graph. One thing that's nice to remember about this equation is if you have v naught plus v divided by 2, same thing as multiplied by half, that's like the average velocity. So this equation really is just the average velocity times the time. And that should make sense. Velocity times time gives us how far we're going. Because we're accelerating, we got to take the average. All right, so let's clear this off, and we're going to write our first 2 equations and then show you how we get the next 2. All right, our next equation, we're going to get through some math. And then we'll show you how it relates to one of the graphs we got from the lab. What we're going to do is we're going to do substitution. You know, when you're solving systems of equation, you use substitution, elimination, graphing, matrices. This time we're going to do substitution. What we're going to do is we're going to take this v in this equation here, and we're going to take the v from this equation. Let's see, get another color here. This v here, and we're going to substitute the at plus v naught in for this v. So all we're going to do is going to take the equation 1, substitute it into equation 2. So what that looks like is we're going to have delta x equals 1/2 v naught, and then instead of writing v, we're going to write at plus v naught from over here. So at plus v naught. And then we just have the t left over on the outside. And we're going to simplify this. See how there's like 2 places to put v naught? There's 2 t's. We can simplify this. So first thing, we're going to combine like terms. We have 2 of these v naughts in here. So we have delta x equals 1/2 2 v naught plus at times t. Next thing we're going to do is we're going to distribute the 1/2 through. The order that we do this doesn't really matter, but I'm just kind of doing it step by step so you can see. So 1/2 times 2 v naught is just v naught. 1/2 times at is just 1/2 at. And we still have this t on this outside, and this whole thing is still equal to delta x. The next thing we're going to do is we're going to distribute that t through. So multiply t by each of these terms on the inside. We're going to have v naught times t plus 1/2 at squared. And now this is starting to look like a quadratic. There's one other thing we're going to change in order to how we write it. We're going to write x minus x naught, because that's delta x, change in position, final minus initial, is equal to v naught t plus 1/2 at squared. I'm going to move the x naught over to the other side, so I have x equals v naught t plus 1/2 at squared plus x naught. And then the last thing, I'm just going to reorder this. So like in your math class, your quadratic is y equals ax squared plus bx plus c. I want it in the same order. So for the final equation, which I'll write up here, we have x equals 1/2 at squared plus v naught t plus x naught. And this is actually the equation for our parabola on a position versus time graph. So we could have a parabola that looks like this. That equation could describe that parabola. We could have, a graph that looks like this on position versus time. That equation could describe this. So this is our third equation, and this is the quadratic, and this is kind of the more complicated version that we got from the lab report. All right, and lastly, we need to get equation number 4. And this equation is going to be something we call time independent. It's not going to have time. We're going to do the same thing as we did before with our substitution, except we're going to solve this equation for t, and then plug that into this equation too. So if I solve this equation for t, I'm going to get v minus v naught divided by a equals t. So subtract v naught from both sides, then divide both sides by a. Then I'm going to take this t here, so v minus v naught divided by a, and plug it into equation number 2. So I'm going to have delta x is equal to 1/2 v naught plus v times v minus v naught divided by a. So I have sort of 3 things multiplied together. I have the 1/2, the v plus v naught, and then this v minus v naught, and then this part divided by a. And you'll just have to take my word for it, but I can take this a here and just move it out to the front, because the order that we multiply and divide things doesn't matter. So I'm going to just make things a little simpler. Write this as 1/2a v naught plus v. You can check this by putting in numbers if you don't believe me. And v minus v naught. So now we gotta FOIL this out. So I have delta x equals 1/2a. And if I FOIL this, I'm gonna get v naught times v minus v naught squared plus v squared, and then minus v times v naught. And we notice we have some like terms. We have v naught v and minus v naught v. So those are going to cancel each other out. Some of you may be noticing that, oh, you can just do a shortcut here if you know some of your foiling shortcuts. Just wanted to show you how it works. So then we have minus v naught squared plus v squared equals delta x. And now we're pretty much done. We just want to reorganize it a little bit. What I'm going to do is I'm going to multiply both sides by 2a. Move that over to the left-hand side. So 2a delta x is equal to minus v naught squared plus v squared. And then how you kind of write the formal equation is a little bit of personal preference. This year we're doing 2a delta x plus v naught squared. I added v naught to both sides equals v squared. Notice there's no time in this equation. So for equation number 4, we got v squared equals v naught, or no, how are we writing it? We're writing 2a delta x first, aren't we? So 2a delta x plus v naught squared. So these are our 4 kinematic equations. If you want to know a trick to how to choose which equation to use for a given problem, what you do is you look at the equation and you figure out what variable is not in there at all. So the first equation, there's no delta x at all. The second equation, there's no acceleration. Third equation, there's no final velocity. And the fourth equation, there's no time. And then what you do is you look at your problem, you make a list of what you know and what you want to know. And then you pick which variable you don't want to know and you don't care about, and you use the equation that doesn't have that variable. Again, you find out which variable you don't know and don't want to know and use the